All right. Okay. 10th week Friday. So congratulations. It's your last day. Is it anybody like graduating? You are. Yay. All right. Congratulations. Did you swim in the is the inverted fountain up?
Construction.
It's under construction?
Yeah.
Oh my gosh. When are you going to have your little pool party? That's a thing, right? It wasn't a thing during online school, but it should be a thing. Is the water on? Life is hard. Okay, well, we'll pretend. Okay, well, congratulations, and I'm proud of you. Okay, let's. So again, bonus content, not on the final. I think it's kind of fun. It's kind of cool. If you're going to be in my 101C this summer, sorry, you're going to see this again. But I think that's only like just a few of you, so I don't feel too terribly, okay? All right, so we talked about decision trees on Wednesday. And decision trees, they're easy to follow, right? It's easy enough. You could put it in the newspaper and, people won't get confused. Whereas, things like, even like a box plot, and we're so accustomed to box plots, like that's like something that requires, a few paragraphs of explanation for someone uninitiated, right? So a decision tree, on the other hand, is just kind of like follow the path and answer the questions, and where do you end up? And people can do that, right? But with the decision tree, its predictive performance isn't great because you're limited to however many leafs you have. That's basically the maximum number of predictions you can possibly make, right? So it works great if you have like a simple categorical variable where it's like you're going to end up in one of three categories. Sure, that decision tree can work pretty well there. But for some kind of numeric variable where you're trying to predict the value, maybe not as great. And so far, between Wednesday and today, I'm only looking at like a numeric regression type decision tree. You can also have decision trees for classification. So we have a few methods that improve the decision tree's performance, but they come at the expense of interpretability. And so the first is bagging, and I'll talk about bagging because we got to understand bagging before we get into random forests. And so random forest is kind of the more popular method, and random forests are built out of decision trees, and they use bagging. And so let's talk about what bagging is first. Okay, bagging is basically applying Bootstrap to a decision tree. And so I think most of you took my 102A class, and we talked about Bootstrap, but in case you didn't take my 102A class, did you still learn about Bootstrap? No? Maybe? Okay. Well, anyway, it's the idea that you just kind of randomize your training data, you resample it, with Bootstrap, you resample with replacement, and this produces a new sample of data that's similar but a little bit different from the original set of data. And because you're resampling with replacement, some of your values will show up in duplicate, but that's a feature, not a bug. And then now you have this resampled data, and you're going to train a decision tree based on this resampled data. And what this does is it introduces variation. It introduces variation into the thing. Kind of like in a family, you have siblings, and the siblings are basically bootstrapped versions of their parents, children, offspring, right? It's just randomized selection of genes and chromosomes from their parents. And so among siblings, you're going to have variation, okay? But the siblings will also end up being quite similar to each other. So that's kind of natural bootstrap in the real world. So so what we would do is we would just create a whole bunch of these decision trees via bagging. Okay, so bagging is, we bootstrap, we make a tree, and then when it comes time to make a prediction, we have your test observation, and you run it through all of the different decision trees that were created. Each of them makes a slightly different prediction, and then you take the average. Okay, so it's kind of just like, you could imagine a family with several siblings. You ask all the siblings, what is your decision? What number do you predict based on these kind of things, based on the input variables? Everybody makes a slightly different prediction. You say how much do you think this product should cost? And you say, it's this big and it's this. And they say, I think it's going to cost this much money. And then you just take the average of everybody's answer, right? So you have a bunch of these different trees. Each tree comes up with a slightly different answer, and then you take the average. And that's going to be the prediction that we do, okay? And so just to illustrate this, we'll do visit our toy example. The toy example, the X values are 1, 2, 3, 4, 5. The Y values are 1, 1, 3, 7, 8. And we are going to do bagging. So first, I'm doing this very manually, just so you can see what happens. So I'm going to select 5 rows via bootstrap, so with replacement. And so when I select 5 rows at random from the pool, 1, 2, 3, 4, 5, I ended up selecting 2, 3, 4, 4, and 5. I ended up selecting row 4 twice. I didn't select row 1. And so this is my data set, okay? X is 2, X is 3, X is 4, X is 4, X is 5, and the values are 1, 3, 7, 7, and 8. And I say, let's make a decision tree based on this. And we'll just keep it simple. We'll just make a single split. What's the decision tree? And if we go through the decision tree process, at what split will we minimize the resulting sum of squares or maximize the reduction in the sum of squares, it says do the split at 3.5. Okay, values less than 3.5, you would predict the value 2. Values greater than 3.5, we have 7, 7, and 8. We would predict 7.33. Okay, and that's going to be the split. So we're going to create a split at 3.5 here. Okay. We do this bagging process again. We resample our original 5 values. And when I resample the values, this time I happen to select row 3 twice. I did not select row 2. I got 1, 3, 3, 4, and 5. And the values are 1, 3, 3, 7, and 8. So where do we make the split? In this case, we're also going to make a split at 3.5. When we make the split at 3.5, values less than 3.5, which are these values, we would predict the average of 1, 3, and 3, so 2.33. And then for the values greater than 3.5, so 4 or higher, we're going to predict 7.5. So these are our 2 predictions. Okay. And then lastly, I'm going to just do it one more time. So we're going to have a simple example. So here I'm just doing 3 bagged trees. In reality, you'd probably do, a dozen or 100 of these things. You'd create a forest of these trees. Now, by coincidence, I happen to select row 1 3 times and row 4 2 times. That was my selection of 5. And that's just by coincidence. And so here, I would do a split somewhere between 1 and 4. Like 2.5 is like exactly halfway in between 1 and 4. And then basically the values less than 2.5 will predict 1. The values greater than 2.5 will predict 7. Okay? And that's exactly what we get when we do this. Okay? So we would split in between 1 and 4 at 2.5. For values less than 4, we predict 1. For values greater than, values 4 or greater, we predict 7. And that's it. Okay, and so those are our 3 trees. And let's say we have a test case where x is equal to 4. So we run this test case through all of our trees. So our first tree with x equal to 4, we would predict 7.33. For the next tree with x equal to 4, we would predict 7.5. And for the last tree with x equal to 4, we would predict 7.0. So these are the values from the 3 different trees. We would average these outputs. We would get 7.278 or whatever the average of these things, 3 things are. And that's how bagging works. So we use Bootstrap to randomize and just get slightly different outputs for trees. And because of the random selection process, you could end up with, different looking trees. So that's bagging, okay? Now, bagging in of itself is usually not enough to, bring about the improvement in performance that we want. And so we extend this process into the random forest. And so bagging randomizes the observations that we use in the training data. And with random forest, we add even more randomization, and we randomize the variables that we could use in creating the tree. All right. Now, I don't have examples here because in our toy data set, we only had one predictor variable, and that was X. But you could imagine a data set where, like at the housing data set, and you want to predict the sale price of a house, and you have different variables, the square footage, the number of bedrooms, the number of bathrooms, the, rating for the kitchen and the rating for the floor, and this and that and this and that, okay? And random forest would randomly select and say, hey, you get to make a tree using these variables, square footage, the rating of the kitchen, and this other value, okay? And then random forest would say to another tree, okay, you get to make a tree, but you're not allowed to use square footage, but you can use the number of bedrooms, and you can use the number of bathrooms and maybe the basement size, okay? The trees randomly get assigned which variables they are allowed to use in the tree making, okay? Why would we do this? Well, bagging tends to produce overly correlated trees. So even though you're bootstrapping the data and randomizing the observations that end up in your data set, the trees that you end up making end up looking very, very, very similar to each other, okay? Kind of like siblings in a family, okay? Because you're starting with the same original data, and you're ending up with just kind of re-randomizations of these things. So they end up looking very kind of similar to each other. And that leads to kind of overfitting, right? So if there's any unusual features that are present in the training data set, okay, that maybe doesn't generalize to the test data or real world, that ends up being part of the model, right? So it's kind of like selecting one family, even if they have a lot of children, and you say, well, this is going to represent all of humanity to the, it's not going to be a great scenario there, right? Because they just look a little bit too similar to each other, okay? Another issue is that sometimes some of the variables in your data set are so strongly correlated with the response variable that every single decision tree ends up using this variable as maybe like its initial split, okay? So you could think of, for housing price, maybe square footage of the home is such a strong predictor that every single tree that you create, the first question is the square footage of the home over 1,200 square feet or something, okay, or something around there. And maybe that number is a little bit different, but the first question is always based on the square footage of the home. And thus all of your trees end up looking almost identical, okay? So random forest says you're only allowed to use certain variables. It randomly selects which of the variables are used, okay? And thus any one of these individual trees are quote unquote impaired, right? We're basically tying one of, one hand behind their back for each of these trees and saying, you're not allowed to use this variable. Even if it's like an important variable, you are not allowed to use it, okay? And what this does is it is going to produce, individually, it might be suboptimal, might not be, the tree all by itself might not perform very well, but it's going to be very kind of diverse, and the result made by the aggregate of all of the trees will end up being better, okay? And so this is a very, very, very silly analogy. You know, you can kind of think of this as, you know, let's say you were putting together a team of people for some kind of mission, okay? And if every single person on your team has eyesight, then probably every single person on your team, you heavily depends on their vision to kind of navigate and get around. Just because for people with vision, eyesight is probably one of their most important senses, okay? But imagine if you included somebody who is blind on your team, okay? This person who's blind does not depend on their vision, and they use their other senses, right? They depend on their hearing, perhaps, and they might have developed some other techniques for getting around. And, you know, there's certainly been a lot of studies and, you know, examples of people who are blind that have learned to use, you know, kind of a form of echolocation to navigate. And you know, fascinating things. They've basically, because these people don't have vision, their senses for, you know, hearing and their other senses are just highly tuned, okay? And so let's say your team ends up in a situation where vision is not very helpful, right? Maybe you're in a very dark cave and you have to navigate, okay? In that case, having the blind person who's able to navigate without vision could end up being helpful. And the idea of the random forest is kind of similar in that, you know, if there's one variable that's a very good predictor and you allow every single tree to use its variable, you're going to become highly dependent on this one variable. And if you end up in some kind of scenario where this one variable actually could end up being misleading or something, all of the trees will end up kind of performing poorly. And so by including other trees that don't use that variable, other trees that are doing their best to make predictions using other variables, you end up getting better performance, okay? By having a large aggregate of a, you know, diversity of trees here. Okay. So random forest would end up working something like this. You start with kind of the bagging process. You're going to do a bootstrap resample of the data, much like bagging. But then when you fit the tree, you just choose a random subset of the predictors. So maybe your original data set has like 30 predictors. You might say randomly select 5 or randomly select 6 of these things. You're going to fit a whole bunch of these different trees. Each tree uses a different random subset of predictor variables, each on, you know, a different subset of the training data. And then when it's time to make a prediction, you're going to feed your test case into all of the different trees. All of the different trees produce different predictions, and then you take the average of all of their predictions, or if it's classification, you take kind of a majority vote there, right? So you know, that's what random forest would end up looking like. Okay, so here's kind of a little diagram that I think I found somewhere on the internet. And so you have tree 1, tree 2, tree 3. This one's a classification thing, but based on the test case, you know, you follow the path of the decision tree, and it says, you know, this is what it this is what it predicts, this is what this one predicts, and then you, if it's numeric, you take the average, and if it's classification, you take some kind of majority vote there, and that would be the prediction, and you would have hundreds of these trees. Okay, so just for an example, I'm using this air quality data set. There's a library called Random Forest, and you can just say make Random Forest predict the ozone value based on all of the other variables, and we're going to say you can use up to 3 variables. All right, randomly select select 3 variables out of the data set. I forgot all of the actual details of this particular data set. And this thing ends up making 500 different trees, number of variables things, and then it calculates some stuff. So this is kind of what it is. So here's one example. This is air quality, the first observation in the air quality data set. It's going to use these values, and it's going to say make a prediction on ozone based on the other variables. And here it says the prediction for ozone is 35.958, which is not exactly the same as 41, but that's its prediction that is made. Yeah.
Each split, does it only look at one variable, or can it look at like all 3 variables to make a split?
So each split uses only one variable, but in a normal decision tree, you consider every possible split. So you sort all the values, you consider every possible split, and you look across all possible variables. So you look at all 5 variables, and you look at every possible split. When you do random forest, whenever you consider a split, you're going to look at all possible splits, but only on a subset of the variables. So you're going to say, okay, I'm only limiting myself to 3 randomly selected variables, and we're going to consider every possible split. And of these potential splits, which one maximizes the reduction in RSS? Okay, and it might not be the same one if you were able to look at all possible splits across all possible variables. Okay, and so it's being quote unquote hindered at each step. But again, when you do the split, the question is, is this variable, above this number or below this number? So it's just one variable at a time. But as far as where to make that split, the normal decision tree process considers all possible splits across all possible variables. And with random forest, you're limiting which variables you can look at by randomly. Okay, so that's random forest. Okay, we'll do the boosting slides too. All right. So boosting is another thing that we've used to kind of improve our performance, and we have these packages. And we might have heard of them because we hear like, oh, this package has really good performance, and it's like XGBoost and stuff like that. These are basically versions of boosting that. And so I'll just cover kind of the basic idea of boosting, and I guess XGBoost improves its performance via the use of gradients. I'm not actually 100% sure on the details of it, but if it's using boosting, this is kind of the idea. Okay, so with boosting, all right, well, here, let me back it up. Okay, so with a decision tree, you ask a question, and you ask something like, is x greater than 2.5 or is it less than 2.5? And if it's less than 2.5, we're going to predict the mean of the kind of the values that correspond here, and we're going to say our prediction is 2. And if it's greater than 2.5, we look at the values that fit there, and we say, okay, then the mean of these values is 7.6, and we predict 7.6. With boosting, it's rather than just predicting the mean of the values, using the training data, we don't just say, okay, what are the values that fall on this side of the branch, and let's use the mean there. What are the values that fall on this side of the branch, and let's use the mean there. With boosting, we make just small incremental adjustments. Okay, so it's okay. This is again silly analogy. This is the story of my life. Everything is a silly analogy. Okay, when you are in your car and it's hot, there's a few. I don't know. This is just one thing that's like how I'm different from my wife. When it's hot, my wife turns the air on full blast to like be super cold, and tries to adjust the temperature that way. Okay, and if the car is just a little bit too cold, she turns the heat to like full blast on super high heat. Okay, and it's kind of like there's no happy median type of thing. Me, I'm the cars have the climate control where you just put in the numbers and you put in like 72 or 73 or something. I'm just I'm gonna just put in the temperature to 72 or 73, and I just make very, very small adjustments. I don't like to go full blast either way, hot or cold. Okay, so the decision tree is kind of like full blast in that if it's too hot, full blast cold, and if it's too low, full blast heat. Okay, whereas boosting is a little bit like, if it's too hot, just do a tiny bit cold and then see if that helps. Okay, or if it's too cold, just do a tiny bit hot and see if that helps. And you make small incremental adjustments. And that's what boosting here is. I don't know why we come up with these weird names. But so you choose a learning rate lambda. Okay, this learning rate lambda is often a small number. Okay, definitely less than 1. And you start off where you look at the mean of all of your values, and this is where you begin. You start off in the middle. All right, you start off in the mean. And then you have some kind of, you consider a decision tree, and it's going to be a very simple binary decision tree. Okay, is it too high or too low? And you look at the difference, okay, which is basically the residuals. And you're going to say, okay, according to the residuals, we should move up to here or we should move down to here. But we're not going to move that fast. We're just going to go a small increment to the right or a small increment to the left. And so you update the residuals using the learning rate times basically what the decision tree by itself would say full blast heat or full blast cold. And here you're going to say, no. Multiply by lambda, which is basically just increment a tiny bit heat or increment a tiny bit cold. And then you do that. And then you iterate again. You just say, okay, did that help? And if it helped, then great. And you go through the process and you say, okay, let's increment either a tiny bit heat or a tiny bit cold. And you do small incremental adjustments. So let me go through an example. So boosting learns slowly, okay, in that we fit small trees each round. So the small trees in of itself, each tree sucks by itself, but you have a whole bunch of these working together, okay? And it trains on the residuals. So it says, okay, after you implemented this thing, how much of a difference do we make? What are our new kind of residuals? What are our new errors? So we're going to do this toy data set. And for the sake of our example, we'll use a lambda of 0.3. In general, lambda is like 1%, a lot smaller, okay? But here I'm going to use a lambda of 0.3, which still illustrates what's happening because it's a lot less than 1. But yeah, in general, it's probably like 1%, okay? And here the number of boosted trees I'm going to do is like 2, versus in a real boosting model, you'd probably have thousands of these things. But we're kind of doing this incrementally, and thus, the resulting boosted fit is going to be bad, but at least gets you started on the idea of how this process is working, maybe, I hope. All right, so here's our training data, 1, 2, 3, 4, 5 for X. Y is 1, 1, 3, 7, and 8. And we say, okay, well, what is the mean of all of our values? The mean of all of our Y values is 4. And so we're going to start off at 4, and we're going to say, okay, what are the residuals? So compared to 4, these values over here have -3, -3, -1, and the values over here have residuals 3 and 4. And we're going to say, okay, let's fit a decision tree to this thing. Now, the decision tree would say, okay, if you are less than 4, or basically at x, the split happens right here between x being 3 and 4. So if you're 3 or lower, let x less than 3.5, then the residual we would predict is -2.33, okay, and that's going to kind of get us in the middle of these values. And the residual on this side would be plus 3.5. And so we'd start off at 4, and the decision tree says, oh, add 3.5 to 4, or subtract 2.33 from 4. And that would be that. With boosting, we say, okay, we don't want to do full blast heat or full blast cold. Let's just do a small increment, okay? Normally 1% or something around there, we're going to do 30%. So I'm going to do, my predicted value here is going to be 30% times what the tree says, okay? So we're going to do, so our new prediction, we start off at the value of 4, and we're going to do plus 30% times -2.33, or 4 plus 30% times 3.5. And so our new predicted values will be 3.3, 3.3, 3.3, and 5.05 and 5.05, okay? Versus if we did full blast, according to the decision tree, we'd end up at 1.67 and 7.5. Okay, so now that we have this, we say, what are our new residuals? Okay, the new residuals between the starting value and what we predicted, we get -2.3, -2.3, -0.3, 1.95, and 2.95. So we're going to fit a decision tree to just these new residual values. Okay, and if we look at these, the decision tree is also going to make a split at 3 and 4, between 3 and 4, and it's going to say, okay, well, so here's kind of the new, just taking that last column, we're going to say, okay, let's make a split at 3 and 4. The value that's between 1.95 and 2.95, I think, is 2.45. And I don't know what the mean of these things are. -1 point something, -1.63. Okay, so 2.45 and 1.63. Our split here is still at 3.5, which isn't exciting. Okay, but we're going to take this and we're going to not add this to our residuals. We're going to temper it down using our learning rate of 30%. So we're going to say, take our old prediction, 3.3, add 30% times what the decision tree predicts, okay, and add 30% times what the decision tree predicts over here, using that new, using that split at 3.5. So here we get 2.8, 2.8, and 5.785. What are our new residuals? Our new residuals are now -1.8, -1.8, 0.19, 1.25, 2.215. So we're going to take this column. This is okay, what's happening as far as just adjusting things and recalculating our residuals. So we're going to take these values again, the residuals, and we're going to say make a decision tree, okay? And at this point, our decision tree is actually going to make the split no longer at 3.5, but between 2 and 3. We're going to make a decision tree split at 2.5. And at 2.5, it says, okay, well, the value you're going to predict is -1.81. And over here, the average of these values is 1.21, basically. Again, we temper this, and we multiply it by 0.3. Okay. So again, each time, we're just slowly incrementing. We're just adjusting the heat a tiny bit up or a tiny bit down, not full blast, high or low, which is what the normal decision tree would do. And so this ends up being the values, okay? So we would predict 2.267, 3.172, et cetera, okay? And so we have three of these unique values. Okay. And that's basically how boosting works. And obviously, this is our toy example and not very interesting. In R, there is GBM. This is going to use, this is our boosting package. And I can tell R to use the exact same settings of making 3 trees total with a shrinkage rate or learning rate of 0.3. These are not good settings, but by telling R to use these settings, we'll reproduce the same values that we did manually here. So if I tell R, here's my data, I want 3 trees total and a shrinkage of 0.3, it's going to create this boosted model, okay? And with the boosted model, we can put in predictions and we can say, hey, what are your predictions when X is 1? And it says, my prediction is 2.267, which is what we have here when X is 1. Okay, what's your prediction when X is 3? And it says, my prediction is 3.172. And what's your prediction when X is 4? And it says 6.147, okay? And so we could trace back and understand exactly where it's getting these values. Now, in real life, these are such terrible settings for a boosted model. You would generally have, hundreds of trees and have a shrinkage rate of maybe something around 1%. And then when you put in your predicted values, it's going to make much better predictions. Okay, it's going to make much better predictions. But maybe a little bit of the problem, and I've got to figure out what the right balance is in 101C, is sometimes when you just have this thing and you just throw in values and it produces stuff out and you have no idea where these things came from. And you have kind of this black box thing. So hopefully these slides explain a little bit as far as where these numbers come from. And you can just imagine, okay, we're just going to push that number from 3 to 300 and push that shrinkage number from 0.3 down to 0.01. And I can conceptually understand where these numbers are coming from, even if I'm not going to manually build out, 300 of these trees to get this exact thing, right? So all of these tools are really only possible today because of our ability to use the computer that can, create hundreds of these trees very quickly. But there is a starting point that hopefully we can understand where it comes from. Okay. Oh, this would be a plot. So this plot is so terrible, just because these are the 3 predicted values. But again, yeah, slow learning process, and that's that. Okay, but that's a little bit of boosting to illustrate where it came from, and that it doesn't have to be such a huge mystery about how these boosting packages work, and because the performance is very good, but a lot of times it's all shrouded in mystery as far as where these numbers are coming from. All right, well that's all I have for you. We have a question?
A question.
Yeah.
So like for boosting, you start with fitting a decision tree with the Y values, and then after that you fit decision trees on the residuals?
Well, no, you're fitting a decision tree. I guess your baseline is predicting the mean. So you have all of your Y values, and you're going to take the mean of all of your Y values, and you're going to say, my very first prediction is just the mean. Do I need to make adjustments to this thing to get better predictions? Yeah, I need to either go up or need to go down. And so you're going to fit decision trees to the residuals from the mean. And so the residual decision tree will say, hey, the mean on everything on this side is over here. The mean residual is over here, and so you should go over here and go over there. But boosting just says, okay, I hear what you're saying. I don't want to be over eager. I'm going to just steer a tiny bit to the right, or I'm going to steer a tiny bit to the left based on this. And that's basically what we're getting. Okay, well, that is it. Thank you guys for a great quarter. It's been a pleasure being your teacher. I hope you enjoyed the class, and I imagine everybody in this classroom has already filled out their course evaluation. You guys are I'm preaching to the choir. If you haven't, please do take a couple of minutes to fill out your course evaluation. And if you're watching this video before 8 a.m. on Saturday, and then please fill out your course evaluation. Yes, today is the I guess the last full day, the last evening that you can take to fill out the course evaluation. They do make a difference, so please do that. Congratulations to those of you who are graduating. You've done a great job, and we're all so proud of you. And add me on LinkedIn. I always love to see where students end up. I like to kind of follow just the professional trajectories and stuff. And don't ever be embarrassed about like your jobs or anything like that. Just we're proud of you no matter what. And that's all. So thank you, and good luck, and congratulations to our graduates. So that's all.